We've sent people to the moon and rovers to Mars. We've peered into the farthest, darkest corners of the cosmos. But there's one frontier we've barely even scratched. The very ground beneath our feet. It's a journey of nearly 4,000 miles to the center of our planet, a hidden realm of unimaginable heat and pressure. The deepest hole we've ever drilled, the Kola Superdeep Borehole in Russia, only punched through about 7.5 miles. Now, that's a staggering achievement, but it's just 0.2% of the way to the Earth's core. It's like trying to understand an entire apple by only piercing the very outer layer of its skin. So if we can't there, and we can't send a probe, how do we have this incredibly detailed picture of a fiery, liquid outer core wrapped around a solid metallic heart? How do we know what's 4,000 miles down? Well, for over a century, scientists have been using the Earth's own immense power to their advantage. They figured out how to turn the entire planet into a giant medical scanner, using the violent force of earthquakes to X-ray its hidden depths. And what they found was a world far more complex and dynamic than anyone had ever imagined. For most of human history, what lay beneath our feet was a total mystery, a blank space on the map filled in by myths and wild speculation. People imagined a hollow Earth, a popular 17th century idea, or just a vast, fiery abyss. Without a way to see, there was no way to know. The problem seemed impossible. The deeper you go, the hotter it gets, and the more intense the pressure becomes. The crust we live on is, on average, only about 19 miles thick beneath the continents. Below that, you hit the mantle, a layer of hot, dense rock nearly 1,800 miles thick that flows like incredibly slow-moving asphalt over millions of years. Just getting through the crust is a monumental challenge, let alone reaching the core, which starts almost 1,800 miles down. Down in the outer core, temperatures can hit 9,000 degrees Fahrenheit, and the pressure is so crushing it would squeeze any probe we could build into a speck of dust. This realm is completely beyond our physical reach. For early geologists, it was a tantalizing puzzle. They knew massive was down there. The planet's density and magnetic field proved that, but they had no tool to investigate it. The heart of our own planet was as alien as a distant star. The first step to solving this problem wasn't building a better drill, it was finding a better way to listen. The big breakthrough didn't come from digging, but from watching the aftermath of the planet's most destructive events. Earthquakes. Thousands of them shake the globe every year. And while they can be devastating on the surface, each one provides a fleeting, precious glimpse into the Earth's interior. They're like a colossal flashbulb, illuminating the entire planet from the inside out. When an earthquake hits, it doesn't just shake the ground in one spot. It releases a massive burst of energy as seismic waves, which ripple out in all directions and travel through the planet. By the late 1800s, scientists had developed the first seismographs, incredibly sensitive instruments that could detect and record these waves, even after they'd traveled thousands of miles. Suddenly, humanity had a new sense. For the first time, we could hear the vibrations of our world. Scientists set up seismic stations all over the globe and started collecting these planetary echoes. They realized the waves were telling a story. How fast they traveled, the paths they took, and where they popped up on the other side of the world was all determined by the material they passed through. The Earth itself was the medium, and the secrets of its structure were encoded in these vibrations. The impossible journey to the center of the Earth could finally be taken, not with a ship, but with science. So, how do these waves actually let us see underground? Well, imagine you have two kinds of secret messengers that can travel through the Earth. P waves and S waves. P waves, or primary waves, are compression waves. Think of a slinky. If you push one end, a compression pulse travels down its length. P waves do the exact same thing. They push and pull the rock they move through. They're the fastest seismic waves, and they can travel through just about anything, solids, liquids, and gases. S waves, or secondary waves, are different. They're shear waves. Imagine taking a long rope and whipping one end up and down. The wave that travels down the rope is a shear wave, where the motion is perpendicular to the direction of travel. But here's the most important thing about S-waves: their critical weakness. They can travel through solid materials. They cannot pass through liquids at all. This one simple fact would become the key to unlocking one of the Earth's greatest secrets. When an earthquake happens, it sends both P waves and S waves rocketing out in all directions. As they travel, they encounter different layers. Just like light bending when it passes from air into water, seismic waves bend, or refract, and change speed as they move between layers. They also reflect off the boundaries. Scientists could measure the time it took for these waves to arrive at different seismograph stations around the globe. By comparing the arrival times and the strength of the waves, they could start to map the path they must have taken. As geologists collected more and more seismic data, a very strange pattern started to emerge. For any given earthquake, there was a huge area on the opposite side of the Earth where S waves were simply gone. They never showed up. This became known as the S-wave shadow zone. There was only one logical explanation for this massive shadow. The Earth's center must contain a huge liquid sphere that was stopping the S-waves in their tracks. This was the aha moment. It was the first definitive proof that Earth has a liquid core. Based on the size of this shadow, scientists calculated its size: a colossal ball of molten metal about 1,400 miles thick. But the story wasn't over. There was another, more subtle mystery. P waves also had a smaller shadow zone where direct waves didn't show up, and yet faint P waves being detected inside it. It didn't make sense. Then, in 1936, a Danish seismologist named Inge Lehmann was poring over the data from a major earthquake in New Zealand. She was fascinated by these faint, ghostly P-wave arrivals at stations in Europe. Others had dismissed them as noise, but Lehmann had a revolutionary idea. She theorized that these waves weren't errors at all. Instead, they had traveled into the liquid core and then some kind of boundary deep within it. Her hypothesis? That at the very heart of our planet, inside the liquid outer core, there was separate core, and this one was solid. This solid inner core was reflecting P waves back out, causing them to appear in the shadow zone. Her meticulous calculations, done entirely by hand, showed that this model perfectly explained the weird data. Inge Lehmann, by carefully listening to the planet's echoes, had discovered the Earth's solid, fiery heart. Thanks to these seismic X-rays, we now have an astonishingly clear picture of our planet's core. The outer core is a churning, turbulent ocean of molten iron and nickel, about 1,400 miles thick. Temperatures here soar between 7,200 and 9,000 degrees Fahrenheit. The constant, violent motion in this liquid metal, driven by heat escaping the core and organized by the Earth's spin, generates powerful electric currents. This process, known as the geodynamo, creates our planet's magnetic field. That magnetic field is our planetary shield. It protects us from harmful solar radiation and stops the sun's solar wind from stripping away our atmosphere. Without the liquid outer core, life as we know it probably wouldn't exist. And at the very center is the inner core, a solid ball of mostly iron and nickel with a radius of about 759 miles. The temperatures here are even more extreme, reaching up to 9,800 degrees Fahrenheit, as hot as the surface of the sun. So, why is it solid? The answer is pressure. The immense weight of the entire planet bearing down on the center creates pressures 3.6 million times greater than at the surface. This colossal pressure forces the atoms to lock into a solid state, despite the blistering heat. And recent research shows it's even more complex. Some studies from 2024 and 2025, which analyze waves from repeating earthquakes, suggest the inner core's surface isn't a simple solid ball. It might be deforming over time, with a mushy or varied texture, influenced by the turbulent liquid swirling around it. This incredible engine at the center of our world is still active and evolving. Today, our ability to X-ray the Earth is more sophisticated than ever. We don't just wait for earthquakes anymore. In labs, scientists use diamond anvil cells to squeeze tiny samples of metal to the same mind-boggling pressures found at the Earth's center, recreating a tiny piece of the core right here on the surface. On massive supercomputers, they run simulations, some using machine learning to model how iron behaves under those extreme conditions. New techniques are popping up all the time. One method, deformation imaging, uses hypersensitive GPS data on the surface to measure the stiffness of rock all the way down into the mantle. Some recent studies analyzing volcanic rocks have even found evidence that the core might be slowly leaking some of its metals into the mantle over billions of years, suggesting the layers are more connected than we once thought. Every new method adds another layer of detail to the picture that started with those first seismic squiggles over a century ago. Every earthquake tells a story. By learning to read them, we've uncovered the deepest secrets of our own planet. If you enjoyed this journey to the center of the Earth and want to explore more scientific mysteries, make sure to subscribe and ring that notification bell so you don't miss what's next. We may never physically travel to the center of the Earth. The challenges of heat and pressure are just too extreme. But in a way, we've already been there. We've used science to illuminate its darkest corners and take a picture of its fiery heart. The story of how we mapped the Earth's interior is a perfect example of human ingenuity. It's about turning a destructive force into a tool for discovery and listening to the silent messages hidden in the rumbles of our own world. So the next time you feel the ground tremble, just remember, those same waves are starting an incredible journey, racing through thousands of miles of rock and molten metal, carrying the secrets of the hidden world beneath our feet. And on the other side of the planet, a seismograph is waiting, listening for the echo.